And apparently I'm the first speaker. So I will start first introducing the menu to orient you about the day. We have quite a few talks, and we'll try to cover lots of topics. And I have kind of the easiest talk of the day because I'm just introducing all the other topics that will show up afterwards. As you can see in the program, there is some time for discussions right before lunch and then at the end of both days. But we've usually asked the speakers to stick to 25-30 minutes presentation, allowing for a bit of discussion after each talk. And we'll try to pick up questions from the audience after each and every talk, depending on you, of course. So don't be shy and ask questions after each talk. And then if a topic gets broader and broader, then we can wait for the end of the morning or the afternoon sessions to get a more complete discussions with the other speakers. So my talk is really introductory, so it gives you some orientations on what we mean by pattern recognition, multivariate data representation, and stuff like that. So I'll start with the standard introduction. Oh yeah, I wanted to know who about you know about machine learning already from a technical point of view? Oh, you are all machine learners who are neuroscientists, most of you? The image fuzzy? Yes, but yeah, we'll try to fix that. Something with the beamer, but I have no control. I can only control with the mouse here. So I'm sorry about that. So the first thing I want to mention is the way that the data are represented. So we usually, whatever we do with neuroimaging, we end up with a series of images. So depending on how you view the data, you have a different angle of understanding them. So if you were a IT person, a series of images from a bunch of subjects would be just a 4D volume. That's the easiest to archive. Now, you can also look at it at a 3D array of feature series. That means each and every voxel, like this one, and you have the time course of that signal at one place in the brain, or another place in the brain, you have a different time course. And then actually what will be more concerning the multivariate approach is we're considering the whole image at once, and then we're considering a series of images. And I will explain you why this is kind of critical in the way you see things. I guess if you're doing neuroimaging, most of you have used some FSL, SPM, AFNI. So everyone, pretty much I assume, has done some standard univariate approaches. And the idea with the standard univariate approach is this. You take here the idea that you have a time series of a voxel, and you provide a model. So you are actually providing an explanation, and then you do your testing independently at each and every voxel. Then you, of course, have to account for multiple comparisons. But the key thing here is that you find a mapping from the model, from your GLM, the design matrix you have, to the observed data. So you look if your model fits the data, and then sometimes it does. Well, great, you have an activation. Sometimes it doesn't. The voxel is not responding to your task, or there is no difference between two groups. Now, when we go for the multivariate approach, it's kind of taking things the other way around. Here, the idea is you go from samples, and we consider a sample as the whole brain. So you have a few samples in one condition, a few samples in another condition, and you train a machine to find the link from the images to the conditions. While for the univariate approach, it was you go from the condition and you find the link to the data. So what we are really doing is finding this mapping from the observed data in order to predict something. And to do that, we need to get some data. There is a training phase, which is really the heart of the approach. But after that, the idea is that you could take a new sample and have no clue about its label and predict what should be the label associated with this. So in effect, you can also see this as my new sample. Is it closer to that bunch of scans from condition 1, or is it closer to that bunch of scans from condition 2? This is not a new concept. It's actually emerged quite a while ago and from the IT and engineering field, and the first major contribution for that kind of things was for pattern recognition in terms of recognizing the digits on mail addresses. So they wanted to automatize things. So people handwrite their postcode in small boxes, and then everyone's got a different handwriting. And the idea was, well, if you have thousands and thousands of examples of the 10 digits, then you can find a mapping from all these different shapes of 0, 1, 2, 3, and so on to the actual value, and then you can automatize. So the idea is you train a function that will take all those data to predict the labels, and once you've produced that machine, then you can take a new letter, and that will the machine, the computer will scan the postcode and will be able to translate the postcode into numbers. So that was the one of the main applications, and it's still used. Now the idea is we don't deal with handwritten numbers, we deal with brain images. But so the things is the data are different, but the principle are still the same. So in terms of pattern recognition concepts, so here what we're doing is associating a set of discrete labels, 0, 1, 2, 3, and so on. So that's typically a classification scheme. So you take your data and you put it with a label A, B, C, 1, 2, 3, whatever. So this is a set of discrete conditions, condition A, B, healthy versus diseased. So it's usually summarized by two numbers, -1, 1, that's typically for SVM, 0, 1 for Gaussian processes. It's just a finite set of values. Regression is the idea that you are mapping your data onto a continuous value. So it can be the age of your subject, a score, a level of a disease, though a level could be seen as a classification problem if you have really discrete levels. So the whole idea is really to know if you're working with classification or regression, and sometimes the distinction is not that obvious, except when you are condition A versus condition B, but the moment you have something that is continuous, then you closer to a regression problem. So that's the idea. Now, in terms of machine learning, something you need also to know what we are doing here is called supervised learning in general. That is, you start your training knowing the input and the output. So you know both sides of the machine. You know what is fed into the black box, and you know the output of the black box. And with that, you can train the black box to do the mapping for new data. So it's supervised because you know both input and output. Now you have other techniques that are called unsupervised, where you just know the images, and you say, well, I have this bunch of images, and there are two different groups of data in there. Just find them. So there you're not pointing, you're not providing examples with labels. You just say there are two classes, split them. So that's unsupervised, and that's, I think, something we'll not be covering, or maybe Janina will be covering that a little bit. So that there are just different families of techniques. Supervised, I would say, is supervised relies on you providing the label. That helps the machine. It makes the job a bit easier, but you need to have the good prediction with a good label associated with your data. This unsupervised means it's easier for you. You don't need to give the labels to the machine, but it's a bit more difficult for the machine to find a solution. And basically, they use different algorithms. So this is the overall idea is you take inputs, brain scans, And what you would want to do is predict the label or the score, so something associated with your brain scan. So in effect, if we knew every information in the brain, we would be able to predict exactly what's happening in your brain, and we would know if you are, what you're thinking, if you are healthy or not, your brain is functioning. We're not at that level of details. We don't have a complete mathematical model of the brain. So what we are doing is using just brain scans, images, and we'll fix the shape, we'll use a function and that series of examples to approximate this mapping. How is that working? As I said, you do the training phase on labels. So data, for each data point, you have the label associated. And what the idea of a machine everyone is talking about is a type of function. So SVM is a function. It's this f, and it has some degrees of freedom, some parameters. So we fix the shape of f, and then we need to optimize the parameters of the machine, tweak the buttons of the machine. There are different machines, Gaussian processes. You have different algorithms, but different algorithm means simply a different f and a different set of parameters that we are optimizing. So what we call the training phase or the learning phase is optimizing the parameters of that function such that you get a mapping, put in one data point as an input, and you get a prediction. So the output of the training is the trained machine. So that's the parameters of your machine. Now the second part is the testing or the validation. We'll have lots of discussion about that with Pradeep afterwards. So there you take a test example and you do a prediction for that one. So there are always two phases in machine learning where we're doing the training and the testing, and sometimes validation as well. So that was the introduction. Now, in terms of data, as I said, we're working with whole brain. So if you take the brain, what is on your computer is just the 3D matrix of numbers. And since we are, if you're using the whole brain, you would be using all the values in the brain. You can summarize that as just a vector. So you vectorize your volume. So you may be masking the brain volume into your MRI, and you get a feature vector. So one data point is one brain image turned into a vector. One issue with that is that when we speak in data dimensions, there is the dimensionality. So that's the number of sample. So a data point is the number of voxels considered. And when we're playing with resolutions of images we have at the moment, we are in the tens of thousands or hundreds of thousands of voxels. So a data point has a dimensionality of the number of voxels you're considering, and that's tens of thousands at the least. Now, the number of samples, that is the number of data points, that's the number of scans or images that you're considering, and typically that's less than 1,000. So you have here a kind of a difference in the dimensionality of a data point versus the number of the data points. And I'll get to that afterwards because that can be a bit of a problem. So the idea with a linear classification, and I'll take a simple example with a brain where we are only considering 2 data points because it's easier to plot, but that will generalize to many more dimensions. So the idea here is if you take your brain and you only have 2 voxels, something on the left, something on the right, for each of these voxels you have values. You have class A, class B, class A, class B, and that's sample 1, 2, 3, 4. So because I have just 2 dimension, my data points are two-dimensional, I can plot them. If I have 10,000 voxels, it's a 10,000 dimension space, and it's a bit more difficult to represent in a PowerPoint. So the idea is I put here in 2D those data points. Now the idea is, I need to predict where this voxel, where this sample comes from. Is it class A or class B? So the idea of the training of a linear machine is to put a line across that space, and you are either on one side or the other. And it's called here, I call that a line because it's a one-dimensional object in a 2D space. Now, when we go to a 10,000 dimension space, it's 10,000 minus 1 object, and that's called a plane with many, many dimensions, so it's called a hyperplane, and that gives you this decision boundary. I did it on purpose to go for two-class classification because that's the easiest. You can cut a space in two parts with a plane, and then you are on one side or the other. And the idea of training is simply fixing this hyperplane parameter. So yeah, and linear classification is typically what we are doing. That's SVM in essence. There are other machines using this kind of approach, but that's the idea of SVM. So once you have those samples, you have your data, you can actually fit different lines, or you could put different planes in your data space. That would be separating your training samples. So how you fix those hyperparameters depends on the type of machines that you are using. I'll get back to that afterwards. And now the issue is that when you have more features than samples, as we have here, pretty much you have very few points in a very, very large space. Because if you have 10,000 dimensions and you have 100 samples, that's very sparsely populated, and it's what we call the nilpost problem. So in theory, you could just find every time a plane that goes through it. So we need to find some trick to handle that. So to make things easier, well, a bit like here, instead of using the whole brain, I could use just a few points. You can use a region of interest, so you have fewer features, so you reduce the size. But still, even if you use a small part of the brain, you easily get 1,000 voxels. And the dimensionality issue is less severe, but it's still there. You have other approaches, searchlight, that's locally defined RI, so you go multivariate, but in the local area, and still it's sort of moving this region of interest all over the brain. I'm not sure, will someone talk about searchlight? Yeah, Jessica will. There are strategies to do feature selection, and what I will be introducing, because that's fairly common in machine learning, is the kernel trick. It's this computational shortcut, and it's an efficient solution to this issue. So you probably, if you've played with SVM or read the literature, you hear about the kernel matrix and kernel trick and stuff like that. So I'll try to explain what is this kernel. So I see it as sort of a similarity measure. So the matrix or kernel is simply a square matrix. The idea is that at each and every point in that matrix, you got a number that is built from a pair of images. So the point here, the coordinates in the matrix 7, 3, will depend on image 7 and image 3 in my data. If you go for a linear machine, how you combine those two images is simply using a dot product. So you multiply element by element and you sum it. There are other types of kernels. You can go for nonlinear kernels. There are, I mean, the example with the postcode and the numbers, that you can use nonlinear kernels. In this, in neuroimaging, as far as I know, a linear kernel is usually sufficient because we have so many more voxels than samples. In effect, using a nonlinear kernel is sort of expanding the space and creating an even bigger space. We already have thousands and thousands of voxels. We don't want to make it even bigger. And the advantage is, all in all, this kernel matrix has a size of number of samples times number of samples. So if you have 100 subjects, that kernel matrix is a 100 by 100, and it's literally summarizing all your data in this 100 by 100, even if you have 10,000 voxels per subject. So it's bringing things together, and that kernel will be used by the machine to constrain the hyperplanes. So the idea of SVM, because that's the most famous, so I'm just mentioning it. So it relies on this kernel representation. And the constraint for SVM is maximizing the margin between data points. So here I'm again using this simplification of a 2D space, so 2 features per sample. So the idea is you fix the border, the hyperplane, by maximizing the distance between the closest samples. And the idea is this plane will pretty much be defined by these parameters, W and B. So it's the orientation of that line and how far off you are from the origin. And the idea is that we are in effect constraining this W to be a linear combination of your data. And that comes out of this linear kernel representation. And the name support vector machine comes from the fact that this border will be entirely defined by a few, really a few points. So these few points are sort of supporting the hyperplane that we've been searching. And they will be the one that are defining this W. And so they're called the support vectors, and hence the name support vector machine. And interestingly, if you were to remove all the other points but those 3 ones, you would still keep the same solution. So class prediction, the idea is if you have a few samples, you do your training, you can then get those values. The idea is these weights, because you're using a linear combination of those images. So if you have 10,000 voxels, your weight in effect will have the same dimensionality. So you get 1 number per voxel in your image. So your weight in effect is an image. So your parameters can be represented either using these alphas or the weight maps. And that's something Jessica will be talking about. So it's showing you the weight maps. So when you have a weight maps, you have pretty much 1 number per voxel. Now, when you do your prediction, you take a new example, and then you can, it's not exactly how we do it, but you can interpret that by saying, well, I have my new measures, I have my trained machine, I have my parameters, my weight vector, I can combine it, and then I'll be on one side or the other of my hyperplane, and then I can get a prediction based on that. So in terms of kernel methods, I've just described it as VM. It's what's called the hard binary classification. So it will give you a prediction. You'll be either in class A or class B. So there is no grading in your output. Why is SVM used? Because it's simple. So it's quick to calculate and it's bloody efficient. It works pretty much all the time. Now you have other machines that are more probabilistic, and in general, stuff like Gaussian processes, they are more complicated from an algorithmic point of view, and they are necessarily slower to calculate because you have more parameters to tune. But they are other advantages. Is, for example, they can return a probability of being in one class or the other. And they can also be extended to multi-classes because you would get a probability of being in class A or class B. It's just a number between 0 and 1. And then you can extend that to class A, B, and C in a more efficient way than SVM machinery being more of a binary from the way it's defined. The probability can be useful, for example, when you are dealing with patients, because having a probability of 55% of being diseased is not necessarily very convincing. If you do a hard threshold, you are diseased or you're healthy. Now, if you are at 55, well, yeah, maybe I should just test it a bit more or try something else, go for further examinations. There are, of course, other approaches, deep learning, tree-based methods, and stuff like that. So these are just some fairly common algorithms, but I'm sure each of the speakers will have their own favorite machine. I think Vince Calhoun, at the end of the day, will talk about deep learning. The validation principle. So the idea is, overall, again, there'll be a talk about that later on, is that you take your sets and you will usually, if you have thousands and thousands of samples, like for the postcode, then it's easy to split it in two very large different sets, and you do your training. So here even if you only have a few dozens of subjects, you split them between training and testing. So what you do is you train your classifier on a part of your data that gives you the trained machine. Then you apply the machine on the untouched data, and you get a prediction. And the whole idea now is simply to compare the prediction, the predicted labels with the original labels. And here, for example, there is a mismatch. So there is an error for that sample. So if we have really a gigantic data set, you can really do your training and your evaluation and testing, and you can do that randomly splitting them. Now, when you have fewer data, as we facing generally in neuroimaging, we will proceed through what is called a cross-validation. So we will be rotating the partitioning of the data. And each partitioning will be a sort of a fold. So here you will be training on that part of the data and testing on the blue part. And then the next fold you'll train on another part and you'll test on the blue folds. So this splitting the data and training and testing and repeating, that's the cross-validation scheme. And there are different approaches. You can do that. The simplest would be a leave one out, so you leave one sample out and train with the rest. Or you decide I split it in 10 folds, and it's a 10-fold cross-validation. That really depends on the type of data you are dealing with, and the key thing is you really must ensure that the training and the testing are done on independent data. So you shouldn't have any obvious link or stuff between the training and the testing. For example, in fMRI, you wouldn't split, if you have a block design, you wouldn't be splitting in the block because of the HRF sluggishness. What you have in one scan is actually linked to what is present in the previous scans, while blocks would be more independent. Subjects obviously are independent, unless you have repeated measures and stuff like that. So there you would need to get all the data from one subject out or from a few subjects out. You wouldn't keep a few scans of one subject, like a drug test before and after. You wouldn't leave half of the data from a single subject out and the other half in. So what you can do at the end is when you repeat, you build what is called a confusion matrix. So you have the predicted classes and the actual classes, and you put a number. So if you have your 100 samples, you will have how many times you did actually predict class A when it is actually class A, when you predicted class 1, 0, so class 0 when it's actually class 0. So that's correct accuracies, and here B and C would be the number of times you get it wrong, one way or the other. So you can calculate the class 1 accuracy, number of times you get A over the number of times you should have found it. The same for class 0. You can look at the total accuracy. So how many times did I get it right over my 100 samples? So that's a very simple measures. You have other criteria. You can also look at the sensitivity and specificity of your classification. So if you are looking for disease, are you sensitive or are you specific, or are you hoping for both? So you can also look at the area under the curve. For clinical applications, you would look at positive and negative predictive value. So what is the rate of good predictions whenever I say he's diseased? One thing also to keep in mind is especially when you have unbalanced data. So if you have 100 samples and you have 15 class 0 and 15 class 1, that's called that's balanced. You have the same number of samples in each classes. Now you can easily find yourself in a situation where you only have 20 diseased and 80 healthy. And that's quite an unbalanced data set. Because in effect, at worst, you could have a machine that says that everyone is healthy, and it would still be 80% of the time correct. But it would be useless. But it would be correct from a technical point of view 80% of the time. So in that case, you would want to go for something called a balanced accuracy. You would have, in the case of the 20, 80, and it's always returning healthy, you would have 100% accuracy in one class and 0% accuracy in the other class. So if you take the mean of those two numbers, you have only a 50% accuracy, which is down to the chance level. So it shows you that at least in that case, it wouldn't be working. So depending on what you have. If you do a regression, what you will do is look at the prediction error in a fold. So you would be looking at the target and the prediction. So, and then you can really measure the distance between, if it was perfectly accurate, you would get all the points on that line. So you can measure the distance, and you take the difference between the prediction and the actual measure, you square it, you sum it, and you take the mean. That means mean across all folds. So it's the out of sample mean squared error. You can also look at the correlations between those points. So that's criteria you can use to validate, to get an idea about the quality of the predictions of your machine. Now, the tricky bit is to know if your accuracy is significant. Are you above chance level? Is my machine doing a good job, or is it just tossing a coin every time? So the one approach, again, I can't remember who will be talking about the permutation. Yeah, no, it's Karsten, yeah, later on. It will get back on this. So just to give you an idea, is the idea with this non-parametric approach is if there is no link between the feature and the target, so there is nothing to learn, so the label are completely arbitrary. So I could just reshuffle the labels randomly. So I can do my training with the true labels. So I have my data and the labels, or I can just reshuffle the labels. That it doesn't matter. So every time I have this either true labels or permitted label, I can calculate the accuracy of my machine. And in effect, this will give me the distribution of accuracies under the null. And then you can provide a p-value for your the accuracy you are observing with the true labels. So you count the number of times you get an accuracy higher than what you observe with the true labels when you are using permuted labels, and that will give you a p-value. And there, again, you can threshold. But there, the threshold is about the quality of the prediction. It's not a map. It's just one number for your trained machine. So I'm getting just right in time. So conclusion, I'll just put here in two columns. The key thing is lots of people are used to univariate and they're trying multivariate things. And there are fundamental differences between these things. That's what I was trying to highlight here in this talk and what my colleagues will be explaining for the rest of the day. So literally the key thing is univariate works with one voxel at a time. Multivariate, you work with one volume. Then the idea is you know the design matrix and you see how it fits the data, while here we go from the data and we try to predict the target. So here, in effect, you're looking for differences or correlation, and here you're looking for similarity or score. So you're doing a prediction. Is this sample from that class or that one? So I see that as a similarity. There's for a difference. Here you use typically the GLM. In multivariate, you have a whole bunch of machines, SVM being one of them, and there are other solutions coming in. It's typically it depends on how those machines are interfaced for the neuroimaging community and what works best for the type of data we're dealing with. In terms of training, in univariate, you do a GLM inversion, so you estimate the parameters and the error terms. Machine training, you get the parameters of your machine. In univariate, you would, in terms of inference, you would look at the contrast of interest. You look at the effect you're interested in, and on the other hand, multivariate, you will estimate typically the prediction of your machines through a CV. And key is here you are doing an inference over voxels. So you have some way of knowing where there is an effect. So I would say it's localizing where in the brain there is something happening with a univariate approach. While here, the multivariate, it's the prediction over the sample. So it's using your image. So there is no localization. There is no way of knowing, oh, this is this part of the brain. No, you are predicting a label for the brain, not where in the brain you have that label. Yep, so that's summary of things coming up. Cross-validation, permutation, weight maps, some bold, some fMRI with Joe and Bertrand, multi-subject, multimodal, some applications, interpretation. So that will actually extend all the topics I've just barely touched upon in this talk. Thank you.